This example says to evaluate the definite integral from -1 to 5 of 7 minus 2x squared dx using the Riemann definition of the definite integral. So we've gone ahead and written out the definition of the Riemann integral, which is the limit as n approaches infinity of the summation from I equals 1 to n of f of x sub I times delta x. Now what we want to do is we want to go ahead and calculate delta x, which is b minus a over n. Our b value in this scenario is 5, and our a value is -1. And so we find that our delta x is 6 over n. Now we want to find x sub I. The formula for that is a plus I delta x. We know our a value is -1, and we just found our delta x value to be 6 over n. And I like to write this as -1 plus 6i over n, like that. So that is our x sub I. Let's come back over here, and we can take the limit as n approaches infinity of our summation from I equals 1 to n of f of, and I'm going to go ahead and replace x sub I with what we just found it to be, -1 plus 6i over n, and then multiply by the delta x that we just found, which was 6 over n. So now I'm going to do two things here. The first thing I want to do is I want to factor out the 6 over n. Now this is a constant in terms of the summation because 6 over n does not depend on our index I. However, it is a variable in terms of our limit, so you want to make sure that we're factoring out 6 over n outside of our summation, but not outside of our limit. And then we still have the summation from I equals 1 to n of, and then the other thing I want to do is I want to take our x sub I that we found, and I want to plug it into our original function. So in my original function, anywhere that I see an x, I want to go ahead and replace it with the x sub I that we just found. Okay, from here we want to go ahead and simplify the expression that is inside of our summation. So I'm going to go ahead and I'm going to square this expression. So if I square -1 plus 6i over n, that is going to give me 1 plus, oh actually that will be minus 12i over n plus 36i squared over n squared. Okay, so continuing on simplifying the inside of our summation, if I distribute the -2 in, we'll get 7 minus 2 plus 24i over n minus 72i squared over n squared. And notice we have our constant term here, 7 minus 2. I'm just going to go ahead and simplify that to be 5. Now that we have simplified the inside of our summation, we can use these summation formulas from our theorem to expand this into multiple summations. So I have the limit as n approaches infinity of 6 over n times, I'm going to go ahead and write my first summation from I equals 1 to n of 5 plus, another part of the theorem for our summations is that we can factor out the constant. So I'll factor out 24 over n outside of my summation. And then the last summation, again, I'm going to factor out minus 72n squared, and then I have my summation being I equals 1 to n of I squared. Okay, So now at this point, we can go ahead and do some more simplification. So let's start off with this summation here. Because we are summing a constant, that is going to turn into 5n. And then I'm going to copy down my 24 over n. The summation from I equals 1 to n of I, that turns into n times n plus 1 over 2. And that is just from our theorem. And then the summation of I squared, that's going to turn into n times n plus 1 times 2n plus 1 over 6. So notice that we don't have any sigma symbols anymore, so we've gone ahead and simplified by removing our sigma symbols and replacing them with the formulas that we have. I'm going to do some simplification here, so n divided by n, and then 24 divided by 2 would leave us with 12 there. And I can get rid of one of these n's, and I would have one n remaining in the denominator. All right, so now what we want to do is I'm going to go ahead and distribute this 6 over n into all of these. And so my first term would be 30 because the n's would divide out. 6 times 12 is 72. And then, oops, I forgot an n here. And in the last term, if I distribute, this 6 and this 6 would divide out. And then I think this is going to become a squared here, so let's write that out. Minus 72 times n plus 1 times 2n plus 1 over n squared. Sometimes folks like to do this, so if I take my fraction inside of my parentheses, I can break that up into two different fractions just to kind of see how that will evaluate in terms of the limit. And then in my last term, I'm going to factor out this 2 right here. And if I do that, I get minus 72 times 2 times n plus 1 times n plus 1/2 over n squared. And so now, as I take the limit, I'm going to have 30 plus 72. This expression here will all go to 1. And so 72 times 1 is 1. And then this here, if we were to take the limit of that, it's a quadratic over a quadratic. And so we just need to take the ratio of the leading coefficients. So it'd be minus 72 times 2 over 1, if you will. And so we get 30 plus 72 is 102 minus 144, and then that ends up giving us negative 42. So there is our final answer.